Hello guys, my name is Lazaro and today we're going to be doing a LeetCode problem. This problem is called implement trie, aka prefix tree. A trie, pronounced as trie as I just said it, a prefix tree is a tree data structure used to efficiently store and retrieve keys in a data set of strings. There are various applications of this data structures such as autocomplete and spell checker. Implement the trie class. So a nice little definition on what we are or what are we doing, what data structure we want to implement, and then here they're actually telling us what are the functions or the methods that this class should have. So the trie initializes the object, inserts the string word into the trie, search returns true if the string word is in the trie, and false if word is not in our trie tree. It then starts with, it will return true if there's a word within our trie that has the prefix prefix. And if there's no word that has that prefix, we return false. So there's a couple of examples down here, but it's one of those examples where it's pretty annoying to look at. So I'm just gonna go straight into the doodling. So let's say we're given a word, a couple of words actually. You know what? I'll start drawing everything in blue, change things up. Say we're given apple, and let's say we're given apron. There we go. So this trie is first going to be initialized with an empty node, and the reason why we want an empty node is, let's say we didn't start with an empty node. Let's say our first node in this tree represents the A character. In this case, this wouldn't be an issue, but let's say we also had another word called blue. Well, this A, we don't want it to point to blue, because if we were to build out a word by following this path, there is no word that's AB. So B should not be a children of A at all. This should not be an edge. So instead, we can fix this by just having an empty node as our root. And then that empty node can go to A, and if we had another word that starts with a different character, it could also go to B. So you can pretend this empty node is just an empty string. So if we were to follow this path, we just have the word B. In this path, we have the word A. So that's why we're choosing the route of starting with an empty node. In this case, this empty node only has one child, which goes to A. The reason for that is because if we're inserting apple, let's say apple is the first word we insert, we want each node to represent a character in the word. Now this is a little hint that we have to create another class. We can call that class node. And we want to hold a couple of attributes. Number one, since these nodes represent the character for this word we're inserting, we want this class node to have an attribute for that character. We can just call that value. And in this case, for this node right here, that value will be A. Now something else we want to, another attribute that we want this node class to have is the next. So A can go to P, can go to R, or it can go to D. There we go, arc. Took me a while to come up with a word with an A and followed by an R. And then with a D we can do a door. So if we have these two words, then A can go to P, because AP in apple, then AP in apron. AR for AR in arc, and then AD for the AD in a door. So we want, since it can have multiple children, keep in mind this is not a binary tree, this is an N array tree, where N represents multiple numbers. It could be 1, it could be 2, it could be 5, right, and so on and so forth. So we want to keep track of this next, or the children for this current node. Now, since all these nodes are going to be lowercase English letters, we can have next be an array of size 26, because there's 26 characters in the English alphabet. Or what I like to do is create it or set it as a hash map. Now, something else that we want to, another attribute we want to give all these nodes is if a single node we're currently on, if it represents a word. Now, why is this important? Well, let's carry on. Let's fully build out this tree right here with this apple and apron. I wonder if I can go back. No, never mind. Okay, looks like we're keeping this square surrounding apple. Let's build out apple. P, then goes to P, then goes to L, then goes to E. Now let's build out apron. We already have A uh, right after our root node. We already have an A. So this means that we do not want to insert another A. Now this is one of the reasons why it says that it's an efficient way of storing and retrieving keys for a string. Because it takes advantage of the fact that it might have a common prefix with other words. And in this case, AP in apron and AP in apple, they are a common prefix. So instead of adding another A, let's just take the A from apple. We can also take the P from apple. But from here, we need to insert another node that goes to an R for the R in apron. Then from the R, we can go to an O, and then from the O, we can go to an N. Now this is perfect, but let's say we had a third word called app. Here, app, we can go to the A. We don't have to insert another one. We can use the A from apple and apron. We can also use the P because AP is a common prefix in all three words. And now we can use the second P from apple because this new word app is a prefix of apple. So in this path right here, we actually have two words. So we cannot determine when we have fully built out a word by just looking at the last node and checking if that node does not have any children. The reason we can't do that is because although we have the word app in our tree, in our trie tree, P has a children. So if we go by the logic of just checking whether or not a node has children, we will fail to notice that app is a word in our tree. This means that we need to give a new attribute to our node class. Let's just call it done. And initially, done is going to be set to false. But for every word we insert, let's say we just inserted app, we go from A to P and then to the last P. At the last node, we want to change this done attribute and set it equal to true. And I can represent that by just doing a check mark right next to each node that has done set to true. This way, if we were to, for example, run through this tree, we go from A, P, P. Since this node has done set to true, which is represented by this check mark, we know that everything we've built so far, which in this case is just the letters APP, representing the word app, We know that this is one word in our try. If we continue, we add an L and an E. That's another word. So we have apple now. And then once we backtrack all the way to the P, we go down to the R, O, and N. Now N has done set to true, so that's another word we've built. And we get all the words that we inserted in our tree. So these are the three main attributes that we need for a trie tree. So this already fixes, or we already solved this first rule, the insert method. Now let's talk about search. If let's say we just inserted all these words, now let's search for the word arose. Now for arose, let's look at every character. First we're starting at the null node. The first character in arose is A. Well, from the null, does it have a children that starts with that has a node value of the character A? In this case it does, so let's go to that node. So now we're currently right here. The next character is R. Does this current node we're on have a next node? Does it have a children that has a value of the character R? We can do this by just looking at our next dictionary, and we notice that it doesn't. The next one is P and only P. So at this case, since there is no children that has a value of R, we know we can return false. So that's the case for returning false. Now let's run through this for searching the word app. We're still starting on the null node. The first character is A. We asked ourselves, well, from this null node, can we reach A? Does it have a children that has value of A? In this case it does. So we go to that A node. The next character is P. For this node that has a value of A, does it have a children that has a value of P? In this case it does, so let's go there. And then finally, it has another P. So does this node that has a value of P, does it have a children that also has a value of P? It does. So we go there. And now we're done. We have no more characters left to look at for our word that we want to search for. That means on the last node we finished on, we ask ourselves, is done set to true? In this case, since it has a check mark, it is set to true. Therefore, we know that the word app is in our tree. Now, if the word we were searching for was APPL, then after seeing the P, we would have checked if P has a children that has the value L. In this case, it does, so let's go there. And now we're done. So we ask ourselves the same thing. Is this node, its done attribute, is it true? If it is true, then we know we have this word in our trie tree. But in this case, since it doesn't have a check mark, we know it's set to false. Therefore, we want to return false because that represents that this word is not in our trie. That's the requirement for search. Returns true if the string word is in the trie, i.e. it was inserted before. APPL was never inserted before, but app was. So that's why app returns true and APPL returns false. Now the final one is starts with, where we want to return true if there is a previously inserted string word that has the prefix prefix. So now let's say, start from the beginning once again. Let's say our prefix is APR. we still start at an empty node. The first character we want to go to is A. Can we go from this empty node to a child that has a value of A? In this case, we could, so let's do that. The next one is P. We could do that because it has a child with a value of P. And then the final one is R. We can do that, so let's go to the child node that has a value of R. And now we're done here, but that's not all we want to do. We want to return true if there's a word that has this prefix, and false if there's not a word that has this prefix. So what else do we have to do in this case? Well, this path that we've taken so far is exactly this prefix APR. And now all that we left to do is to run DFS on this last node. And if we reach a node that has done set to true, then let's return true. Because that's telling us that there's a word that has this prefix. In this case, if we run DFS from the R, we go to O, from the O we go to N, and we notice how N has a check mark, which represents that done is set to true. So we want to return true, that there is a word that has the prefix APR. And now that is the last thing this problem is asking us. Now the first one is just to initialize it, and we can simply initialize it by just creating this empty node. That's all we really need to initialize it. Once we call the class, we have to create this root node, which is an empty value. So let's get to the coding and solve this question. Like I said, one of the first things we want to do is create that node class. So here I'm just creating its constructor, and I'm going to give value a default value of an empty string. Then self.next is going to be equal to a hash map or a dictionary in Python, and self.done is going to be set to false by default. Then here in the constructor of the Trie class, we want to create that root and set it equal to node. And since I'm not passing any arguments, that means this argument is going to take the default value of an empty string. Next, let's work on the insert method. Let's say current is equal to self.root. And then for every character in word, let's check if this node is already in our trie tree. We can do that by just calling cur.next.get character. And if that character is not a children of the current node we're on, let's default to creating a node for this character. Whoops. Else, if it is a children, then we could retrieve it, and let's just retrieve the node of that children. Now we can do cur.next for this character, set it equal to that node. And once again, if this node is in our tree, we're just resetting it. We're just re-adding it to our next dictionary. It's not really going to change much. But if it's not there, then it's going to create a new node, and now we're adding it for the first time. The last thing we want to do is set cur equal to node, because now, since we're going one by one through every characters in this word, then we want to add the next character in the word to the current character we just added. Then the final thing is set cur.done equal to true. At the end, cur is going to be equal to the node that represents the last character in this word. And since it's the last character in this word, then we want to set done equal to true. Now we want to do something pretty similar for searching. So I'm just going to copy that and paste it right here. Else, what we want to do, instead of creating a character for the word we're searching for, let's default to returning false if that character is not in the children for the node we're currently on. And if not node, let's return false. And instead of adding it to the children's list, let's just set cur equal to node. And then finally, after all is this, all we have to check is if the last character in this word we're searching for, check if that is done. So just return cur.done. This will be true if we have previously inserted this word we're searching for, and it will return false if this character does not represent one full word in our tree. And now for starts with, we want to do pretty much the same thing. Cur is equal to self dot root. And then for every character in the prefix, let's just do cur dot next dot get that character, or default to false. Now, if not node, we also want to return false, because that's saying that this prefix, the character for this prefix, is not even in our trie tree. Therefore, we know for sure that no word is going to start with this prefix. Else, cur is equal to node. Now, after this for loop, cur is going to be equal to the node that is the last character in this prefix, and that is also in our tree. So all that's remaining is for us to run DFS from this node and try to see if there's a node that has done equal to true, has the attribute done set to true. So let's just return self.dfs of this starting on this current node. And let's build out this DFS function. Now if node.done, so if that's true, let's return true. Now if length of node.next, if there's no children, if that's equal to 0, let's return false. Else we want to, if none of those ifs hit, what we want to do is create a variable called answer, initially set it to false, and then for every character and next node in the children of this current node, answer is going to equal to answer or self.dfs of next node. And then finally, let's return whatever answer is. So if at some case in this DFS we did return true, answer will be updated to true, and that would propagate all the way through the recursive stack call. And finally, we will return true here if we did find a word that has this prefix. Else, we would just be returning false. So now let's run this code, see if I made any mistakes. Okay, looks like indentation is out of line. Yeah, it is. Oh, I think it's here, actually. Yeah, it's there. Let's run it one more time. Perfect. Let's try some more test cases. Actually, there's only one, so let's just submit. And it gets accepted. Perfect. So hopefully you guys are able to understand what a trie tree is now. And you guys know how to implement this very important methods, which is inserting, searching, and starts with. For most trie problems, the one they're going to be using most often is the inserting, and probably this starts with. For most problems I've done that does require trie. There's a whole bunch of times where I do need to run this DFS given a certain prefix. And of course, every single time I'm doing a trie, I need to first insert the word into my trie. And then comparing search to these other two methods, it's the comparing search to these other two methods, it's the one that I've implemented the least. Because of course, for searching, you could just add all these words that you've inserted to your tree into a set, and then just return true if word is inside that set of the words you've inserted. But other than that, hopefully you guys enjoyed. If you did, please leave a like and consider subscribing. And thank you guys for watching.